Hello friends, welcome to another video of Zeta Axis, and today we will discuss about seafloor spreading theory. Seafloor spreading theory is one of the three important theories explaining how different structures are formed on the surface of our Earth. In previous videos, we have already discussed about continental drift theory, in which Wagner described that the continents move over oceanic flow. However, he failed to give any force or mechanism causing this drift, and therefore his theory got rejected. In 1929, Arthur Holmes came up with convection current theory, where he said that there lies a convection current within the mantle of our Earth, and it is because of this convection current our continents move. However, his theory was also incomplete and it could not answer all the questions related to continental drift. In 1943, sonar technology came into existence due to World War II, and using this sonar technology in which sound waves are directed towards the seafloor and the time for its reflection is observed, and using this, the oceanic floor map was developed. So in 1957, Mary Tharpe was the first to develop the oceanic flow map using this technology, and this led to a very huge change in our understanding of the oceanic flow. When this mapping was done, we found that there exists a long chain of mountains across all of our oceans, as you can see here. And these long chain of mountains had a rift within them. So basically, there were two mountain chains with a rift between them. Now, this disapproved or this proved wrong all the conceptions we had till now for oceanic flow. Now, there was a new structure of seafloor available, and scientists and geologists started to think about how this kind of seafloor structure was formed. And it was then when Hess gave this seafloor spreading theory in 1962. The seafloor spreading theory word consists of two words, seafloor and spreading. The word seafloor is pretty obvious. It means the landmass under ocean, which we can see in the blue color. So this is all the landmass that is under oceans, which is called seafloor. The second word means spreading, that means expanding. So we can see in this animation that the seafloors are expanding. The red color line indicates the mid-oceanic ridges as discovered by Mary Tharpe, and all the other colors, as they get darker, they shows the seafloor aging. So we can see that the seafloor is younger when it is closer to this line, and then it gets old. So this is what basically the seafloor spreading theory is all about. It says that the seafloor expands. In the figure, we can see a map of ocean floor developed by Mary Tharpe. Now, this kind of map led to new structure of our oceanic flow, where we can see that there was a mid-oceanic ridge in the middle and trench on the sides. Now, geologists started to give different theories about how these structures could be formed. And one such theory was given by Harry Hammond Hess in his book, History of Oceans in 1962. Now remember, while Harry Hess gave this theory, it was an observational theory. It was not a scientific theory based on scientific laws or something. This was basically an hypothesis which he made based on his observations. So let's discuss what did Harry Hess said in this paper, History of Ocean Basins for the origin of our seafloor. So first he says that there lies a convection current as discussed by Arthur Holmes within our mantle. Now, this convection current rises up. It is very hot. And when it reaches till the crust of our Earth, it starts to diverge into two parts and flows into two directions. Now, because it is hot over here, it starts to melt the oceanic crust, as well as because they are diverging in two different directions, it applies a diverging or splitting force on the overlying crust. And therefore, slowly over the time, this crust starts to divide from here. The magma, which is below here, starts to come up. And over the time, we can see that because of this diverging force, as well as hot magma, which is rising above here, it starts to slowly melt this crust and it starts to make its way to the surface of the crust. While doing so, we can see that the mountain structures are formed on the rift which is generated, and slowly over time this magma is able to come to the surface. Now when this magma reaches the surface, it starts to cool down. And when it cools down, it forms new structure over here. So we can see this magma from the mantle comes up, it melts the crust, it comes to the surface, it cools down and forms new seafloor. So this is how Harry has said that the magma comes to the surface and forms new seafloor. Now as the new seafloor is formed over here, the old seafloor is pushed away. So we can see that these structures are moving away from the mid-oceanic ridge. Here in this animation, you can see that the seafloor acts like a conveyor belt, where the seafloor structures are moving away from mid-oceanic ridge on both sides. So both sides are having a mirror-like structure, where they are moving away from the mid-oceanic ridges slowly. Now let's try to apply the theory given by Harry Hess to these seafloor structures of Atlantic Ocean. In our Atlantic Ocean, we already know that there lies long chain of mountains, which is thousands of kilometers long, and it extends from Antarctica to Greenland. These long chain of mountains have a rift valley within them. So if we see the structure of the seafloor, it would be something like this, where there will be a mid-oceanic ridge with mountains on both sides, and within it there is a rift valley running all across this mountain chain. So as Henry has suggested, that magma must come out from this rift valley and it should cool down to form the new seafloor. And as new magma comes up and forms new seafloor, the old seafloor must be pushed away from the mid-oceanic ridges. To understand it better, let's look at the cross-section of our Atlantic Ocean. So here we can see that this is our asthenosphere. The magma rises from here and reaches the surface through this rift valley. We can see that this rift valley exists all along this mid-oceanic ridge. So the magma comes up here, solidifies and forms new seafloor. Now if we take this map in which age of seafloor is represented by the color, the red color indicates youngest seafloor and the yellow line indicates older seafloor. So we can see here that the seafloor which is closer to this line is young, and the seafloor which is away from this line is older in age. Therefore, the seafloor must be formed at the mid-oceanic ridge and slowly pushed away as suggested by Harry Hess. Now if you see the map of ocean floors all across the world, we can find mid-oceanic ridges in all of them. All Pacific Ocean, Atlantic Ocean and Indian Ocean have mid-oceanic ridges. And if we see the age of seafloor, we can see that the seafloor age closest to this mid-oceanic ridge is youngest, while the seafloor away from this mid-oceanic ridge is of more age. Therefore, the seafloor must be formed at these ridges all across the world in all oceans. Now we have discussed so far that how seafloor is created at the mid-oceanic ridges. But if the seafloor was to be continuously created at the mid-oceanic ridges, then there exists two possibilities for our Earth. The first one is that the Earth was continuously expanding, which means that over the time our Earth's radius should increase because the Earth is continuously expanding as the magma comes from the mantle and cools down to form new crust. So the crust should become thicker and thicker. But this was not the case. No geological evidence was ever found about our Earth continuously expanding. This led to a second conclusion, that is the seafloor must be continuously destroyed. So as the seafloor spreading theory says that the seafloor is continuously created at the mid-oceanic ridges. So to balance that, the seafloor must also be continuously destroyed somewhere. In the next part, we will discuss how these seafloors are continuously destroyed. So we have already seen that this seafloor is formed at the mid-oceanic ridges, and over time it travels from this mid-oceanic ridges to the edge of our seafloor. It takes around 200 to 300 million years for the seafloor to move across the seafloor. Now during this time, the rocks in the seafloor which are formed here, they cool down, and as they cool down, they become more dense and their weight increases. Therefore, the rocks over here have much higher density compared to the rocks over here. Therefore, the weight of the seafloor over here is very high. Secondly, in this 200 to 300 million years of time, a lot of sediments is deposited from the continents on this seafloor, increasing the weight of the seafloor. Therefore, it adds to the already high weight of seafloor in this region. And a third factor comes into being where this descending magma, which is very hot over here, cools down slowly as it moves and descends. Now, because it cools down, it forms a layer beneath this seafloor, and you can see formation of this layer over here. So this layer also adds to the weight of seafloor over here. Because of this heavy weight, this seafloor will start to descend, and this weight is called slab pull, or the force which is created by this weight is called slab pull. There exists another region for descending of this seafloor within the asthenosphere, and that comes from the mid-oceanic ridges. As new magma rises and new seafloor is formed over here, the new seafloor pushes the old seafloor away. So there exists a diverging force at the mid-oceanic ridges which pushes the seafloor away, while the slab pull is there which pulls this slab downwards or pulls the seafloor downwards within the asthenosphere. And it is the combination of these two forces due to which the seafloor descends in the asthenosphere, as we can see over here. So finally, it will descend in the asthenosphere and get destroyed. So this is how the cycle of our seafloor is maintained. The seafloor is formed over here. In 200 to 300 million years, it moves across the seafloor, and here it comes and descends. And while it descends, it forms a trench over here, which is a very deeper part in our seafloor. Now, if we see the map of our Indian Ocean, we can see that there exists a mid-oceanic ridge over here. And a trench is there at the boundary of this Sunda Island, which is called Sunda Trench. So basically, the seafloor is created over here. In 200 to 300 million years, it travels across, descends in the trench and gets destroyed. If you see the cross-section of Indian Ocean, we can see that here is the mid-oceanic ridge, which we were talking about. And this seafloor moves across, reaches the Sunda Trench, and then descends into asthenosphere. So this is how the seafloor of Indian Ocean is formed at the mid-oceanic ridge and destroyed. Similarly, oceans across the world are formed at the mid-oceanic ridge and destroyed at some trenches. Now, we have already discussed that when Hess gave this theory, his theory was basically an hypothesis without any supporting evidences. But later on, around in 1963, just after he gave seafloor spreading theory, a mapping of magnetic anomalies was done on seafloor. And this proved to be a very good evidence for seafloor spreading theory. So let's discuss what was this magnetic anomalies and what it stood for. Now we know that the magnetic poles of our Earth continuously change their location. They can move from one place to another. And because of this, the magma which comes to the surface of our Earth, it has a very large amount of magnetic elements like iron and nickel. These magnetic elements are randomly oriented when the magma is very hot. But as the magma cools down, these magnetic elements align themselves and they point towards the magnetic north pole at that time when the magma solidified. Once they are solidified and formed into a rock, these magnetic elements are locked into its position. Now, even if the north pole, that is magnetic north pole, moves away from its position, these elements will continue to point in their old directions. Similarly, even if this landmass is moved due to continental rift or other processes, still these elements will hold their position. Now in this diagram, we can see a seafloor where there is a mid-oceanic ridge and magma is coming out from it. The magma which comes out from this rift valley or from this mid-oceanic ridge, it solidifies on both sides. The solidified rocks have their magnetic elements pointing towards the magnetic north pole at that time period. Now over time period, what happens when new magma comes up and solidifies? Then it points towards the magnetic pole at that time. we can see that at the seafloor, we can see that different rocks period formed in different time period point in different directions. So by studying the magnetic elements of these rocks in the seafloor, we can find the path of the magnetic North Pole. Now what happened in 1963 when the mapping of our seafloor was done, it was found there exists magnetic anomalies on the seafloor, where we can see that the rocks in the seafloor, their magnetic elements alternately point in opposite directions. That is, one stripe points in the upward direction while the other stripe points in the downward direction. And this is symmetric on both sides of the mid-oceanic ridge. So you can see here that the first layer is green pointing downwards. Even here, the first layer is green pointing downwards. So what this meant was that the seafloor was not created altogether, but it was created stripe by stripe, because the rocks which were formed here, they were formed when the magnetic North Pole was over here, while the rocks of this stripe were formed when the magnetic North Pole was over here. So basically, this suggested that the seafloor was not formed as one single structure, but it was formed stripe by stripe. And on both sides, the stripes were similarly formed. So this indicated that the seafloor must be formed over here and then slowly moved away from the mid-oceanic ridge, as suggested by H Hess. And therefore, this was a very big evidence for his theory. Now, when age mapping of seafloor was done, it was found that the age of rocks close to the mid-oceanic ridge was very less, and the age of the rocks increases as we move away from the mid-oceanic ridges. And this happened symmetrically on both sides of the mid-oceanic ridge. So here we can see that these stripes on both sides of the mid-oceanic ridge has same age. And similarly, the similar color stripes have same ages. So we can see that the age pattern is repeated on both sides of the mid-oceanic ridge, and the age increases as we move away from the mid-oceanic ridge. Therefore, this was also evidence which supported seafloor spreading theory. There were certain other evidences which were collected later on to support the seafloor spreading theory, one of which was heat floor map. Now, we know that this convection current brings heat from the deeper parts of our Earth, and this heat, when it comes to the surface, is slowly dissipated to the space. You can see in this animation here that in the form of radiation, the heat from our interior parts is dissipated. But if we see, the large amount of heat is dissipated near the mid-oceanic ridges because the crust is very thin over here. And as we go away from the mid-oceanic ridge, we see that a very less amount of heat is dissipated to the space. So this kind of amount of heat dissipated by the seafloor was mapped, and we got this kind of structure. We saw that large amount of heat was dissipated at the mid-oceanic ridges, while very less amount of heat was dissipated at the edges of the seafloor. So this also proved seafloor spreading theory, that the crust is very thin at the mid-oceanic ridge, and that is why a lot of heat is dissipated over there, while it is thicker at the boundaries of the seafloor, and therefore very less heat is released to the atmosphere from the edges of our seafloor. Now, another evidence which was used to support seafloor spreading theory was study of gravitational anomalies. In this study, what we do is that the gravity of an area is calculated by a model, and this yellow line you see gives the gravity from that model, which is a constant line. Now we know that gravity of any place depends on the amount or the type of material which lies beneath that area. So when actual measurement of gravities are done, which is indicated by the red line, we can see that the measured gravity is much above the gravity from the model over here, because the continental crust is very thick over here. As we come to this region, over the trenches, the measured gravity is very less compared to the gravity given by the model. When we come to the mid-oceanic ridges, we see that there are mountain structures on the seafloor over here. Therefore, the gravity given here by the measurement is equivalent to the gravity given by the model, and so on. So basically, what was done in the field, that gravity measurements were done all across our globe, and anomalies were detected. These anomalies indicate that the amount of mass or amount of crust thickness or other things beneath that region. When we see the gravitational anomalies all across the world, we see that at the mid-oceanic ridges, because of the mountains, the gravity is very close to the gravity given by the model. But as we move away from the mid-oceanic ridges, we see that the anomaly increases because of the trenches, because of the subducting plates. So even this kind of mapping or this kind of gravitational anomaly mapping supported the seafloor spreading theory. I hope you liked this video, and if you have liked this video, then please like, subscribe and share. We are going to make full coverage of geography and other subjects for UPSC. So please subscribe our channel and please press the bell icon. Thank you.